but OpenStax covers it, so we'll cover it too. And some of the OpenStax stuff is new to me, but let's see what we got. So the sheet I gave you kind of organizes solids, so I like it. All right. So solids can either be crystalline, and we have all sorts of options here, or they can be amorphous. Check out amorphous is kind of a dead end, right? If it's crystalline, then things are organized. If it's amorphous, things are chaotic. Okay, that's about it. The amorphous solids have no orderly structure. I'll go ahead and let you know the biggest common amorphous solid would be plastics. We understand the repeating unit in plastic, but the way it's arranged in its solid state is kind of mixed. The other type of, or another common amorphous solid would be glass, just like plain old glass. How it breaks, who knows? Okay, it's not well defined how it's going to fracture. Okay, so crystalline or amorphous. So crystalline, amorphous, right? I mentioned that plastic is amorphous, kind of how these stack. They're long, kind of repeating units bonded to each other, and then those repeating units are stuck together. So here we have, these would be crystalline solids, and we have different types of crystalline solids. Okay, so it can be a molecular, ionic, network, or metallic. Here is silicon. This is aluminum, and this is salt. So we have talked a lot about molecular compounds. So if I'm looking at crystalline substances, you're like, really? A molecular crystalline substance? Yep. Okay. How would those molecules be held together in their solid state? By hydrogen bonding. Water in its solid state is a type of molecular crystalline solid. We sometimes have molecules held together with dispersion forces or ordinary dipole-dipole. Now these have general characteristics, and I think I listed a few. They have regular, IM means intermolecular bonds, an example is water. And if you wanted to, you could add to this. I don't know if you need to necessarily, but they're generally soft. They have low melting point temperatures, and they don't conduct electricity. So there's water, cute little water molecules lined up, all stuck together in their solid state. Carbon dioxide, iodine. See, this goes pretty fast. Moving on to type of, yep, there it is, network. Okay, what does that look like? And some of this is going to be kind of familiar, or kind of like, oh, that's a very common substance, solid in solid state, and it's a network crystalline solid. These actually are generally hard instead of soft. They melt at high temperatures instead of low temperatures, and they also do not conduct electricity. So examples, we talked about the carbon has various allotropic forms of carbon. Carbon atoms can arrange and make our diamonds. Carbon atoms, remember, also can arrange and make our graphite in our pencils. They can also arrange and make a buckyball. But these actually, you're like, and granted, it's a little squishy to me, because we've talked about covalent bonds versus intermolecular bonds, and you're like, well, what are the bonds that join those carbon atoms together? Okay, well, they are a network of bonds that makes it the network solid that it is. Silicon dioxide, SiO2. Dioxide looks like it's got I don't know. It's trying to show you the repeating unit up there. That's clearly not an SiO2. That looks like an SiO4. But two of those oxygens are actually connected to two of those oxygens are connected to another silicon. But trying to show you the network solid. Silicon carbide, another network solid. And of course the first two kind of go together. With graphite, it's like with diamonds. We have the repeating atom is only one type of element. It's just carbon. We'll get carbon in diamond, carbon in diamond, carbon in graphite. So those are all network solids. It says an infinite, I don't think it's supposed to be infinite, an infinite series of covalent bonds. Silicon dioxide, quartz is silicon dioxide. You can kind of see that, and it is kind of a weird sort of thing. You're like, well, where does it? It reminds me of the formula units that all kind of combine together in ionic compounds to make a crystalline lattice structure. Silicon carbide. There's another allotrope of carbon. All right. I'm not sure what I'm trying to say there. Let's just read the caption. So, with what it's showing you is the pure substance is the kind of that green sort of thing, that green sort of ball, and we have two outliers, and they kind of disrupt the crystal, the network structure, and voids can disrupt the network structure. All right, so that was two. So we did molecular crystalline, and we did network, and now here is ionic crystalline. And that you're kind of familiar with that, where you have cations and anions are alternating, and they make that crystalline structure. In their solid state, they are relatively hard and kind of crunchy. In their solid state, they take a lot of energy to melt them, and they don't conduct electricity in their solid state, but if you dissolve them, for instance, or I shouldn't say dissolve them, in their liquid state, they are pretty darn good conductors of electricity. So this is the Na plus and Cl. Of course, the Cl minus is the big ones because it's picked up an electron, and the Na plus would be the smaller ones. This is a crystalline lattice structure, alternating sodium cation and chloride anion. So there's a little more. Obviously, there's definitely a lot more we could say about ionic compounds. This is kind of giving you a sense for what sort of crystalline form you could expect. And it depends on, like this caption says, the size of the ions as they kind of nest together. And I'm not going to go into it, it's not going to be in your test, but as it turns out, you can kind of generalize the crystalline shape. This one is a cubic structure, and notice this one actually has the cation is very small, surrounded by the anions. And this one, the cation is big, surrounded by, larger cations. They're much larger than the cations. Okay, so it's showing you the anions. This is the anion surrounded by cations. So if they're similar size, you get the previous one. If one's much bigger, in this case the anion's much bigger, you get this as a face-centered cube. And don't worry about this. This is kind of showing you how layers of the ionic compounds can kind of find holes and compact. Right. So we did those three. Onto metallic. These are kind of fun. A metallic solid would just be like stainless steel is an example of a metallic solid. Okay. Actually, just a strip of copper is an example of a metallic solid. So what happens in this case is the valence electrons of the atoms that are bonded together kind of delocalize and form kind of a sea of electrons. That's pretty cool. And that sea of electrons then gives them their awesome ability to conduct electricity. I think that's pretty cool. So your metallic solids, their hardness can vary a lot, their melting points can vary a lot. The thing about metallic solids is they tend to be malleable, means you can hammer them out into a sheet, and ductile means you can pull them out into a wire. Metallic solids conduct both electricity, and generally they conduct heat too. So this is looking at a bunch of copper atoms that are just stuck together. Now you can think of kind of, I'm just going to show you an image here in a minute, of the valence electrons delocalizing from the atoms, as shown here. So if your valence electrons delocalize, kind of dissociate, delocalize, local means they're connected to a particular atom, delocalize means that they're just not connected with a particular atom. It leaves behind something that's kind of positive, the nucleus, the protons in the nucleus, and the non-valence electrons. So it would be kind of a positively charged thing. So OpenStax has this figure to kind of summarize those 4 types of solids, crystalline solids versus amorphic solids. The type of particles that join together, the type of connection between the particles, pretty good. And then generally speaking on each slide what you can expect with regard to a crystalline solid of that type. And there are some examples. So just in case you run into it again. I am getting to one point that actually, I was like, do I really need to do this part? Because I'm like, I don't really put it on the test and everything. But I think it's important for this. We've been talking about boiling point temperatures, and I think you guys definitely have it under your belt. Like if the intermolecular bonds are stronger, that means your boiling point temperature is going to be higher. Well, we have this thing, I like your sheet, by the way. We have this other transition. So boiling is liquid to a gas. Melting is solid to a liquid. Okay, so you're like, well, the whole melting point transitioning, we should expect as the bonds are stronger, then your melting point transition temperature is going to be higher. A similar thing. And there's a little bit of a catch. So by the way, so melting point and melting point temperature means the same thing. It's the temperature at which something transitions from a solid to a liquid. So one of the things, if you go on, especially into organic chemistry, maybe even analytical chemistry, but you're probably going to do some melting points. Okay, and so I'm going to, let's see which one I'm going to show you first. I'll show you this little video first. The solid begins to collapse, and then when it finally finishes collapsing, the range is an indication of how pure your substance is. If it's nice, tight, sort of 2 degrees range, that means that you have a nice pure substance. If it melts over a range of like 10 degrees, that means that your substance is pretty impure, the one that you were running anyway. So melting point, like I was saying, doesn't correlate as well with the strength of intermolecular bonds as boiling point temperatures. And the reason is because not only is it bond strength, but it's also the symmetry of the molecule. And in general, and I always get this wrong, but it kind of makes sense if you read the caption, with symmetry, now this is with solids, with symmetry, basically they stack better, and if they stack better, or the solid kind of stacks better together, that means that it's harder to melt. Okay, so that's a function, symmetry. So the other day, gosh, just yesterday, we were talking about cis and trans, okay, and it's across a double bond. The reason double bonds have 2 sort of isomers, 2 sort of possibilities, has to do with the fact that there's not free rotation around the double bond like there is around a single bond. So I'm not sure if you guys buy this. Let me see if I can find my pen. Because I'm not really, the fact that there's not free rotation means that, first off, these guys are planar. Both of these molecules lie in a plane. Okay? Well, with that in mind, we know that the chlorines are highly electronegative. Okay, so I'm going to just put maybe I'll put partially negative there. I'll put a partially negative here, partially negative there. Okay. And we said that with a molecule, if your regions of negativeness and positiveness coincide, then it's nonpolar. So can you see spatially, if these are the two hot guys, okay, where is the middle of these two chlorines? Right here, yep. So that's the center of general negativeness. And I think I could make, so this is negative. I think I could make a case where kind of the general center of positiveness is also there. Okay, so that's why that thing's not polar. Where is, if these two guys are the hot guys, where's the region of general negativeness, center of negativeness here?
Down between
right here, yeah. So we talked about if they don't coincide, which they don't, here's where then you're going to have a negative here and I would go center of positiveness here-ish, maybe here-ish, I don't know. And so you do have a dipole moment, a net dipole moment. Okay, so that makes that polar. All right, and by the way, can you see where we're dealing with a type of E because it's a double bond, F because there's only two carbons, we kind of start from the back and move forward. Dichloro, there's two chlorines, and they're both on different carbons, so 1,2 dichloroethene. This one is cis, they're both on the same side, and the other one is trans. So when we look at the boiling point temperatures, which one would boil at a higher temperature? Yeah, the polar one. Yep, very good. Sometimes I have to, especially when I have negative temperatures, I have to concentrate. But yes, the polar one boils at the higher temperature than the non-polar. But which ones? Oh, yeah. So symmetry. Let's see if I can erase all my stuff. So on the board, I went ahead and said that with symmetry, they stack and they're harder to melt. So let's see what sort of symmetry we have. We can actually do a point of symmetry. Actually, we can do a plane of symmetry. So this side is like this side, okay? But I couldn't go like this because that side's not like that, okay? I could do a plane. I can't do a plane, can I? But I know it sounds weird. It's hard for me to explain it, and I can't do this way. But I can, on the trans, I can do a point of symmetry. Here's my point of symmetry. I'm equal carbons, hydrogens, chlorines. It's a point of symmetry. So that one's more symmetrical. So harder to melt. And this is where my negative temperatures, I have to picture them on like almost like it's like a timeline, like a number line. Okay, so negative 80.5 degrees Celsius, they're both very cold, negative 50 degrees Celsius. Okay, but can you see where this one melts at a higher temperature? Because negative 50 is higher than negative 80. Okay, so it has the lower boiling point but the higher melting point. And it has to do with the fact that the melting point is associated with it transitioning from a solid to a liquid, and solids actually have an extra element to how much energy you have to pump them in order to get them to transition. It's the element of symmetry, and it was known as a boundary. There's all sorts of little nuances in this unit of material that I'm like, you have to just think about it. Just take your time on the test and just think about it. How does that work? This is showing both melting point and boiling point temperature. Forget about symmetry. This is just showing you one of the things that we know. If you increase, these are all dealing with alkanes. Remember, alkanes are hydrocarbons with all single bonds, hydrogen and carbon. And increasing the number of carbons Notice that the blue line we've been talking about, you increase the boiling point temperature, yeah, and you increase the melting point temperature. So why is that again? What is kicking in when we're getting a larger molecule? What's that? Electronegativity? Dispersion forces, yeah. Dispersion forces that it's easier to induce a dipole on something large. The polarizability is better. Yep. And that would be for, transitioning from a liquid to a gas and also from a solid to a liquid. So, just a few things about these guys. Remember, plastic is a good example, glass is a good example. So these have a wide melting point temperature just because, like the sled, it's not really, it's more random how they're connected, how the repeating units are connected. When they crack in their solid state, they're not going to have a nice clean crack. It's going to be pretty darn random. So, hope whoever broke that glass knew what they were doing. 7 years of bad luck, right? But it's random. So this is showing you kind of the silicon. Wait, this is showing you how you can take something that's amorphic and make it crystalline. And the way they did this, I'll go from left to right. So this is amorphic and this is crystalline. The way they did this was to just to treat it. It's a type of glass. Heat treated, excuse me, heat treated. All right. So these, I do think we're going to get through 3 parts. So far, so good. Sorry. But these will be due, as you might imagine, on Monday. So, yeah, definitely.
Oh, by the way, we're, as of right now, I talked to Sybil in the trio office. She said that we're not, planning right now to leave at 12:30, so I'd be here for half the class.
Okay.
On Monday, and then.
Okay, well that's better. Very good. Okay. Do you have any games coming up, Benny?
We played yesterday, and we're gonna play on Saturday.
Saturday?
Mm-hmm.
Okay.
Yeah, we have 6 games left.
Not very many.
No.
Woo!
It's almost over.
I was gonna say. Oh, you'll miss it. You know you will.
Yeah, I'll do.
Okay. Phase diagrams. They're a little squishy too. They feel squishy to me. Let's see what you guys think. But they're important. This is a phase diagram. They're called pressure temperature phase diagrams. So if you kind of get your bearings, and this is for a particular substance, all pressure temperature phase diagrams would be unique for a substance. So if we look at the 3 physical phases of a substance, this kind of shows you what phase a substance will be at the various pressures and temperatures. Okay? So for instance, if I had, something that was at this temperature and at this pressure, what do you think? It would be a solid, right? If I had something that was at this temperature and this pressure, you see where they intersect, and you understand what physical phase it's going to be. And it kind of makes sense with some of the things we've talked about. So, if we kind of look at that upper sector over there, the way this is laid out, so we have increasing temperature from left to right along the x-axis, and increasing pressure. So I'll do that. So increase this way, and increase this way. Maybe just kind of. So here's the deal. If we take something and we have a pretty darn low temperature, okay, and we have a high pressure, pressures are great at actually squishing matter together, so they go ahead and form those bonds that make them a solid. It's going to be solid. So this is kind of makes sense. Well, what if we have something that is, do the other extreme. This guy down here. Okay, something in this general region of a pressure temperature phase diagram, you're talking about high temperatures and low pressures. So you're like, dude, that is so going to be a gas. And then kind of in between, liquids are always in between solids and gases. What does that mean? Kind of moderate temperatures and moderate pressures. Okay, so all phase diagrams of any substance is unique. So here is, doesn't say what it is. Okay, they kind of form this Y sort of shape too. Do you see the Y? It kind of goes up like that. And we're going to talk about this abrupt stop. The Y actually stops there on the right side. This one I think goes on forever. Okay, and this one kind of, what do you think this temperature right here is?
Question. Is it 0 degrees Celsius?
Zero what? Celsius, Kelvin, Fahrenheit. 0 Kelvin. Yep, that's actually 0.
Ooh, dang, yeah, that's cold.
That is cold. Yeah. So if we kind of look at, again, it's kind of a Y. If you're like, I don't know where to begin with my pressure, temperature, phase diagram. Well, go ahead and get your bearings. Make a Y. It kind of goes like this, and I'll talk more about that in abrupt stop. Goes like this. This is pressure. This is temperature. And you go solid, liquid, gas. That's it. This one kind of goes on. So if you go back and forth between this segment, solid and liquid, you must be, see, solid to the liquid, you must be melting. Liquid to the solid, you must be freezing. Okay? We could kind of do this one, going back and forth between these guys. Like the slide says, liquid to the gas, you're evaporating. Gas to the liquid, you're condensing. So vaporization, condensing. Well, here's one. This is a new one. Okay, you can actually go back and forth from a solid to a gas. And when we talked about that before, we talked about sublimation or deposition. I like this one, sublimation. Something goes from a solid to a gas, it sublimes. Something goes from a gas directly to a solid, it deposits, or deposition. Okay, so that makes sense. And again, for a particular substance, if you're given the ordered pairs for the conditions that substance is influenced by, if you're given the temperature and the pressure, you just plot them on here where they intersect. That's what the physical phase of that matter will be.
The college will be closing at 1 p.m. Again, the college will be closing at 1 p.m. All evening activities and classes are canceled. Please be safe. Thanks.
We can't get a break.
I was just about to say.
But actually, I'm glad they're doing what they're doing. So
it was getting bad, like outside on the ground.
Yeah. Okay. Can we finish this part though, you guys? Okay. How many slides we got?
9.
It's pretty short.
Okay, let's do it. Oh, drat. Okay. All right, so pressure, temperature, phase diagrams for specific substance. It shows the 3 physical phases. I'm going to show you a 4th physical phase that's really exciting. You're like, really? I think of it as a 4th physical phase in the pressure phase diagram. So this is water, and water is weird. Water is weird. This right here, and you guys know how, like, if this is just my XY of anything, this is a positive slope, okay? And this is a negative slope. Are we good with that? Okay, if it leans to the right, it's positive. If it leans to the left, it's a negative slope. Water has a slightly negative slope there. That is so exciting. What that means is that if see here's 0 degrees Celsius. If I'm at 0 degrees Celsius and I go ahead and ramp up the pressure, what's going to happen to my solid? It's going to turn to a liquid with increasing pressure, which is weird. And ice skaters, they do that because their blade has, their pair of blades, whatever, has all the weight of them. And they are connecting onto ice and pressurizing ice. So they are actually making it to a liquid. That is what makes them do their thing. Isn't that cool?
Wait, so like it can be it can still be like below freezing temperature, but if it has high enough pressure.
Yes, definitely, yeah, because this is where it freezes, and if you go from 101 is 1 atmosphere, 101 kilopascals. I wish this was used atmospheres, but this is normal. This is 760 millimeters of mercury. Yep. So if you go ahead and at the same temperature, if you add pressure.
So that kind of explains why it's not a set rule necessarily. Well, maybe one of the reasons why, like, it can be 29 degrees Fahrenheit and there's still liquid water and it's not freezing.
Yeah, I hadn't thought about it, but that would be working that way, yeah. Now that would be the atmospheric. Are you talking about the pressure of the atmosphere, like precipitation?
I guess so, yeah.
Or just in general?
Because like there's sometimes where it's like below 32, but it's not freezing,
Mm-hmm.
and it's like stagnant water. It's not moving. You know what I mean? So it's like probably because it's got like more pressure than usual or something.
No.
I was thinking about the weather too, but I still like, I don't know. I have to think a little bit more.
wet, yeah. I don't know about a puddle, but weather is bad about it. If this is the Earth's atmosphere, and we have a cloud up here that is producing snow, all we have to do is have a warm pocket and then a cold pocket. And that's what gives us freezing rain.
Okay.
Because it melts here and then it refreezes here. Yeah. Yeah, and that's exactly what's going on. It's called a temperature inversion. Yeah.
That's what I was thinking, like about freezing rain.
Yep. And depending upon how much time it has as it falls, you'll get it freezing on contact or you'll get sleet. If you get sleet, it has time to pelletize. But if it's a really narrow pocket, then you're in trouble because it's going to freeze on whatever it contacts. It's almost like super cooled water, and it's like, there I go. Cool. Okay, so on a test, and sometimes, the test isn't made up yet for you guys for next Thursday, but sometimes I will ask, pressure, temperature, phase diagram, what are these segments all about? And hopefully you could tell me the segment B to C, so find B and C, okay? That is actually where, what's in equilibrium? Well, B and C must be gas or vapor and liquid. Okay, they're in equilibrium. And it kind of hurts my brain. I was thinking about this, but the vapor pressure curves we've been talking about? That segment right there, as it's marked from B to C, that is the vapor pressure curve for that substance.
So but the segment is the equilibrium between the two phases.
Yes, it's the equilibrium between the two phases. Yep, exactly. So let's find A to B. So A to B, that was where we have the sublimation and deposition. So that is actually equilibrium between the vapor or gas and solid. If we find segment B to D, you're looking at equilibrium between solid and liquid. So the triple point, is that not an awesome thing or not? I mean, it's so cool. So triple point, you figure that's the intersection or the equilibrium point in all three phases. That one hurts my brain too. You're like, it can all coexist. So triple points, I know.
So what would be like an example of that?
Well, recently, and clear back in Chem 1, because I did it recently in my intro to Gen Chem, we talked about standards, and our thermometers are calibrated according to the triple point of water, which is 1/273.15 units from absolute zero. Bottom line is the triple point for water is, it says, it's basically 0.01 Celsius or 0 Celsius. I don't know. Triple point temperature. But the triple point temperature has to have a corresponding triple point pressure, right? So, because like if I'm at 0.001, if I'm not at 0.6 kilopascals, I'm not at my triple point.
So if we have like water at 0.01 Celsius and 0.6 pressure,
It would be, I don't know. I've never done it. We should look up videos because I bet someone's done it because it would just be coexisting.
Yeah.
I agree. Triple point videos.
You can do it in the lab.
Yeah.
I don't have a good way to draw a vacuum and then to measure the vacuum, but I'll think about it.
I didn't even know that was like a thing, you know?
So the fourth phase kind of comes in here, and it's related to this little abrupt end of the equilibrium between the liquid and the gas. This actually is called the critical point. So the critical point has a corresponding critical temperature we call TC and a corresponding critical pressure we call PC. Go figure. And the OpenStax does it a little bit different than I think I would. But what I would like to do is basically kind of go this way and this way. And all of this stuff, if you have your material is in this region, it is a supercritical fluid. And it's got basically supercritical fluids have properties of being both a liquid and a gas. They have kind of, because they're high pressures, they kind of have kind of the oomph or the heft of a liquid, but because they're at high temperatures, they have kind of the penetration of a gas. There's supercritical fluids. That is so cool. I know. No one else calls it like a fourth kind of phase of matter, but to me, it's kind of got characteristics of two. Okay, I have some more slides to talk about that, but in the meantime, remember the other day when we said if this is our equilibrium vapor pressure curve, we said where the pressure is atmospheric pressure, that is the boiling point temperature. Okay. Well, if we go over here, if this is the pressure of the atmosphere, where this intersects right here, this would be the freezing or melting point temperature. Freezing point temperature, melting point temperature is the same. Okay, so whatever, you have to find the atmospheric pressure over here, you go to where it intersects these two to see where it's going to change its phase, the temperatures. Okay. Again, I wish this wasn't in kilopascals because who does kilopascals? I don't. But that's about 1 atmosphere, 760 millimeters mercury. Okay, so compare the slope, that's water, compare that slope with this slope. Now this looks like it doesn't have a slope, but most substances have not a negative slope like water, but have a positive slope. So that means if you pick any, what's called an isotherm, if you pick any temperature and you increase the pressure and it's a liquid, it's going to go become a solid. Okay. This one is for iodine, and you can see the abrupt end to the equilibrium vapor pressure curve. That's your critical point. And I mentioned before it has a critical temperature and a critical pressure. And beyond that, it's a supercritical fluid. So that's the way I think of it. Now your OpenStax does this, which I don't know, maybe it's right. I guess I have to think more about it. But it has the abrupt end of, I don't like this pressure temperature phase diagram, but it has the abrupt end of the equilibrium vapor pressure curve between the gas and the liquid. And it says right there, anything that is a higher temperature than that is going to be SCF, by the way, it stands for supercritical fluid. Yeah. So I'm not going for this one is for carbon dioxide. All right. Triple points. That's just so cool. Triple point. Everything's in equilibrium. And kind of like the critical point, it's going to have a specific pressure and temperature associated with it. We still got to look into that. Critical points. Okay, it's abrupt end. Critical points are associated with this segment. Okay, and that's where your supercritical fluid is going to begin. All right, so with regard to supercritical fluid, you can get a supercritical fluid this way, I think. If you go ahead and close it and you continue to heat it up. Okay, well maybe that's not what I want to say. I have some pictures coming up, and it kind of describes this. I don't know. So let's say we pick a liquid, okay? Let's say we pick a liquid. I'm going to go with this pressure, okay? I'm going to pick a liquid, and I'm going to heat it up. So I'm going to heat it up, and as long as I allow the pressure to mean this makes sense. Pressure to maintain the same, it's going to go ahead and it's going to gasify. It's going to vaporize. But what if I cap it off? Okay, so one of the things we know about if I cap it off, I think that's what the slide is describing. What's going to happen is the pressure is going to increase and increase and increase. We know that if you heat anything up, the molecules go faster and the pressure inside is going to go faster. So actually what this is describing, you're going to see it here in a minute, is if it's capped off, the pressure is going to increase, and I'm heating up, the temperature is going to increase, and that's where you get something quite easily into become a supercritical fluid.
Is it like when you're like heating water and then you put like the lid on the pot, and it's like it's gonna turn into gas, and then it's gonna like compensate.
Yes.
Okay.
Yeah, I think
And
so.
it's gonna like back and forth like that.
Mm-hmm. Yep, back and forth like that, and then like if you carefully lift up your lid, you'll see condensation on the lid. Mm-hmm. Yep. 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 I think we're okay with this. Critical pressure, critical temperature. So, yeah, I guess OpenStax was okay because according to this, beyond the critical temperature, you're never going to get anything. Well, to me, this is still a gas. You'll never get it to liquefy ever again because it's just too darn hot. If I add pressure, I still say this is a gas. If I pressurize it, it's not going to turn into a gas. Not going to turn into a liquid. It's going to turn into a supercritical fluid. I still say I'm right. So supercritical fluids, we're kind of in that region up there. And like I was saying before, what makes it so cool is it has the density like a liquid, so it has heft. It can pick things up, but it has the permeability of a gas. By permeability, it means it's got low viscosity. That was the other thing I was going to look up. Well, it seems like with the rain, the way we've got it, I think water becomes more and more viscous as it gets colder. It's still liquid. And so you almost see it dripping, and you're like, oh my gosh, that's not good. So supercritical fluids are great for what we say extracting things. They can extract good things or bad things. Okay. So I don't know if you need to fill this in. You got this one. Okay. So this is showing you kind of what I described. I think it's a closed container, and so we have kind of just a airhead space. The thing, you see the liquid right there, and at this point we are below the critical temperature. Okay, we're approaching the critical temperature here, and you kind of see the fuzz right there, where it's starting to kind of be, can't quite tell the difference between the liquid is down here. This is the liquid and this is the gas. And then this last one, this is above or at the critical temperature. So the whole thing would be supercritical fluid at that point. And you can just barely kind of make out the ghosty. What's that?
That's crazy.
That is cool. This one, you got to look at it. It's kind of like the melt temp apparatus that we looked at earlier, where you're looking through a viewfinder, and this is the top and this is the bottom. And here again we have the liquid, and in the liquid we have these two floats floating. Okay, if you read the caption, here we have supercritical fluid. So there's no distinction between the liquid, I'll put gas up here, the liquid and the gas. And I'm not quite sure what this one is, but this one is actually then back, this one is back to the same scenario as this one. but I know this one is the supercritical fluid. I think this one is cooling down. All right, so some substances, what their critical temperature is, what their critical pressure is. Carbon dioxide, I was like, man, you have to heat it up to 304, but that's 304 Kelvin, which you subtract 273 degrees, and you're back to something kind of reasonable. So by choice, carbon dioxide is not a bad one to try to make into supercritical fluid. You can kind of see water. And then this one is showing you the extraction process for beans, coffee beans. So what you do is you take your coffee beans here, you go ahead and let them dwell here. What they're dwelling in is supercritical carbon dioxide. So that carbon dioxide is great at pulling, see, carbon dioxide, that's nonpolar, right? Great for pulling the nonpolar part of the caffeine molecule. Like this says, this is a caffeine molecule. Look for polarity right here, because this is your oxygen, double one oxygen, double one oxygen. Otherwise we have a bunch of, so it's polar, but it's also kind of non-polar. It's got a bunch of alkane part to it. I think those blue things are nitrogen atoms, so that's caffeine. So anyway, it dwells, we have supercritical fluid carbon dioxide coming in, and then the spent supercritical fluid goes out here. Our caffeine is swept away, which this got me to thinking, do you think like the Red Bull and stuff like that coordinates with people who are decaffeinating coffee beans? Because I don't know, they try to use everything possible, but once it's extracted these molecules out, then they're ready to go ahead, and I don't know if it's batched or continuous process, but they go ahead and take the beans out, which now no longer have that caffeine molecule. I think that is so cool. All right, so those two will be due on Friday. Wait, Monday, sorry. So, yep, that's all I got today. Alice?